So, in my last video, I said I'd be publishing these a lot more frequently, and that hasn't really happened. It turns out that isolation's exhausting. I mean, I have been napping a lot, and not just having lots of naps over the past few weeks. I'm having several naps a day. I love naps. I don't know why children don't. I would love to have a nap in the middle of every. I'm getting off topic already. This is ridiculous. So, I thought what I'd do in this video, because I'm still trying to figure out how I want this channel to go. I thought in this video I would give a bit of an insight into what a lesson would be like. So I'm going to give you an online lesson with the AV materials that I would be using, some of the explanation. I've already recorded this once, so I thought, but didn't hit record on the camera. So I hope this will go as well as the last one went, but never mind. We'll find out. Anyway, my name is Reese and I've been a science teacher for 10 years. And in this video, we are going to introduce ourselves a bit more carefully to our home, planet Earth. So let's play a game. Let's try and spot planet Earth. Can you see us? Do you feel invaded? Do you see privacy feel invaded that this picture was taken without your consent? This is a picture taken by the Cassini space probe in 2013, I think it was, looking back through Saturn's rings at Earth, and here she is. Here we all are. These few pixels right here show everything you've ever known, done, or loved. So let's get a little bit closer. In fact, let's get a lot closer, because we don't do these things by halves. Earth is one of the 4 terrestrial planets. We've got Mercury here, we've got Venus, also known as the sister planet to Earth. You can see why they're roughly the same size. Here is Earth, and here is Mars. Mars is quite a bit smaller than Earth, and you can just about make out the poles here. These are rocky planets. Now, as the solar system formed, the area of space where the rocky planets formed was so hot that gas giants like Jupiter or Saturn couldn't form. Only substances like metal and rock could actually stay together under these really tough conditions. So that's why we've got these 4 terrestrial planets that we find between the Sun and the asteroid belt just past Mars. Now, here we have one of the most famous photos of Earth ever taken. This is the Earthrise photo. Again, it's just absolutely stunning. This is what the Earth looks like from the moon. And as you can see, the sky looks black. There are no stars out here because this is daytime on the moon. The sun is lighting up all of this space around here, and we're getting a similar sort of effect to why we see shapes of the moon on the planet Earth here. Can't see the stars because the sun is just too bright. Let's zoom in a bit further. Here we are, Earth's eastern hemisphere. As far as surface is concerned, Earth is over 70% water, and you can see it here. It's all very beautiful, oh lovely, and quite clearly water is blue. People say water is colourless, but it isn't, it is blue. But if you take the volume of this beast into account, water is much, much, much smaller by terms of volume. The Earth is a rocky planet. It is made up of mainly rock and metal. Now, as solid as this looks, there is much more to Earth than meets the eye. Okay, so as I said in that introduction segment, there's more to Earth than meets the eye. So let's zoom in a bit further. We come all the way from Saturn. Let's get in a bit closer. So let's get to the closest part to space. This is the, need to read it, Chimborazo volcano in Ecuador, and it is the tallest mountain on Earth. Don't care what you think about Everest. It's not the tallest mountain. No, it's not. No, it's not. This is the tallest, the Chimborazo. I think I'm pronouncing that correctly. No idea. It's in Ecuador, and if you measure from the centre of the Earth to the top of this currently not exploding volcano, it is the tallest mountain on Earth. It is the closest we can get to space. This is because the Earth, it's not perfectly spherical. It is an oblate spheroid. And an oblate spheroid, you take your sphere and you squashed it slightly. So the equator actually juts out a little bit more and the poles are a bit more flattened. So this means the closer a mountain is to the equator, the more of a boost it gets. So, who knew? Now, obviously, you are much more familiar with this beauty. This is Mount Everest. This is the highest you can get above sea level, 8.8 kilometers above sea level. A pretty impressive number, if you ask me. It's a stunning view. It is incredibly lethal and dangerous to try and climb. Every year the Sherpas have to take down tons of rubbish, and by rubbish we mean air canisters, broken equipment, tents, and unfortunately a large number of dead bodies from people who push too hard and don't make it back. But still, it's an incredible view. We climbed it because it was there. Pretty awesome. So if we go from the highest above sea level we can go to the lowest below sea level, this image is of a road along the shoreline of the Dead Sea. And the Dead Sea is 432.65 meters below sea level. That's where the shoreline is, but that is going down because of irrigation, because of use of water further upstream from the Dead Sea. We are losing quite a lot of water, and it's going down and it's not being replaced. But we can go lower. We can go lower, and this image is of the Denman Glacier. The Denman Glacier is really cool. It's a glacier. It's a flowing river of ice. And because ice is technically a solid, this means anything underneath it is still dry land. So 3.5 kilometers below sea level, the bottom of the canyon beneath the Denman Glacier, that is the lowest land point, the lowest naturally occurring land point on dry land that isn't a cave that you can get to. Now, there's loads of stuff on YouTube that you can search up to find the lowest caves, the lowest drill points. Most of those photos have copyright issues, so I can't use them in this video. Not that I'm bitter, a little bit. Have a look at them. I still quite like being technically right. It's the best form of correct. So we've come from Saturn, we've come down onto Earth, we've gone from the closest part to space, the highest part above sea level, the lowest road, then the technicality of the lowest point below sea level that is still technically dry land. But you can go further than that. So this would be a lesson. So the first thing that I would ask my students to do would be to rule off their work with a pencil and a ruler. If they've got more than half a page, carry on that page. If they've got less than half a page left, start a new page. If they've got approximately half a page, that's a judgment call. And then you put your date down and you put the title. And today we'll start a brand new topic. It is the Earth. This isn't the most taxing lesson, being an introduction. What would I want to get out of it? Well, I'd want you to be able to recall the names of the 4 layers of the Earth. I'd want you to be able to tell me how big they are, what they're made of, some of the simple properties, some of the effects, and I want you to be able to draw a diagram. But before we get there, what we need to do is focus on our technical vocabulary. Being a new module, we need to introduce some new vocabulary that allows us to talk about this information more precisely, more easily, and much like a language, the more you know, the more that you can understand, the more you can appreciate, the more you can enjoy the lesson. So I always start my lessons with a section on key definitions. So I'm going to flash up the key definitions. You're going to pause the video and you're going to copy down the key definitions. You don't have to copy them in different colours. They're there because I have too much time on my hands. But you copy them down into your notes. So here they come. And now you copy them down. Okay, so hopefully you have copied those into your notes. You spent some time getting them in there nicely. And I do find it helpful just to quickly go through them. So the crust is this layer that we stand on, made of cooled rock. That rock is split up into tectonic plates. These are like great big ships slowly floating across the ocean that is the next layer down, the mantle. Now the mantle, it's often called magma, but a better way of describing it is plastic rock that can change its shape. It's very hot at this level, but because of the pressure of all the rock above it, it's keeping the rock as a sort of weird solid. It can move a bit like a liquid. It can have these convection currents where hotter rock is less dense. It rises up through the mantle. As it gets into contact with the crust, it cools down, it becomes more dense, falls back through the hotter, less dense rock, setting up a conveyor belt. And these conveyor belts can move these tectonic plates, these ships, very, very slowly, but very powerfully. They're being moved at the rate your fingernails grow in some places. And these are responsible for some of the most spectacular things on the planet. So we've seen Mount Everest, the Himalayas, tectonic plates. We've seen an inactive volcano, volcanoes, tectonic plates, earthquakes, tectonic plates. They are planetary forces. Huge amounts of energy being expended. I love this topic so much. We'll go into more about these later on, but I really do love this topic. Once you get past the mantle, you get into this core. So you've got the theory, you know what these things are made of. Let's take a look at a diagram. That was rubbish. It's better. So, if you look very carefully, if you lean right the way in, you might have to really come in quite closely for this, guys, because the diagram is quite fine anyway. Boom! Sorry, couldn't help it. I do it to my students in lesson all the time, and I said this was going to be an authentic classroom. Hopefully, I made a few of you jump. But anyway, the crust you can see is this very, very thin layer. It's between 5 and 70 kilometers thick. That's a pretty big range. The thinnest parts are on the ocean crust. They are the thinnest parts, and the continental plates, continental shelf, that is much, much thicker. As I say, these float on a vast area called the mantle. It's this molten/plastic rock that is nearly 3,000 kilometers thick in places. And this then sits on top of the core. Now the core is in two parts. The very center, you've got a vast, vast, vast ball of nickel and iron that is hotter than the surface of the sun. So it's easily hot enough to melt this ball, but it doesn't. And the reason that the ball doesn't melt is because of the enormous pressure. All of that rock, whether it's molten or plastic or cool, all of that pushing down from the outside is enough, even though it's so hot, over 5,000 degrees Celsius, even though it's so hot, it's enough to keep those particles closely enough together so that it remains a solid. Now, as you get further out, you've got less pressure, whereas the heat doesn't drop off quite so quickly. This means that the outer core is actually liquid. It's made of nickel and iron again. And this liquid core, we think, it's not certain exactly how this works, is vital for life on Earth. Can you think why? Think lights in the sky. Think sun having a temper tantrum. Did you say magnetic field? If you did, you were right. If you didn't, that's acceptable. If you're saying that you did and you didn't, you're a liar and you need to reevaluate your life choices. So the moving molten metal sets up something called a dynamo effect. And this emits a vast magnetic field, something like this. And we're back. This magnetic field erupts out from Earth and it protects us from the sun's most dangerous, deadly rays. Things like coronal mass ejections will fire out very, very dangerous particles into space. If they collide with, I don't know, DNA, they can cause huge damage to living things. This is something that we're going to have to figure out how to protect astronauts if we're going beyond Earth's orbit. These coronal mass ejections, these ionized particles, this solar wind, it can damage electronics, it can kill our foodstuffs, and it can hurt the astronauts themselves. So other than at the moment extremely thick metallic shielding, we're still not sure quite how to deal with that particularly long term. This is why the thought of permanent habitation on the moon will actually be in tunnels, naturally occurring lava flow tunnels underneath the surface of the moon rather than on the top, because that would provide the natural protection from the solar radiation. So that this vast molten pool of metal spinning around this slightly less vast lump of metal, life would not exist. This is happening about 3,000 kilometers beneath our feet, and if it stops, we're done for. It also has a few other things. It causes the northern lights, which are pretty. I've never seen them in person because, you know, lockdown. And birds are thought to use the magnetic field to navigate. It also flips regularly, but that is definitely a topic for another video. So, again, I would now give some time for my students to copy down this diagram in pencil, labelled using a pencil and a ruler, and you're letting the labels do the work. It doesn't have to look beautiful and perfect. Smooth, clean lines. And this is an opportunity for some of you with more of an artistic flair to use your gel pens, fine liners, oil, pastel, crayon, tip, belts, whatever it is that you have, to make a really beautiful diagram whilst you do this. So I'm going to bring the structure up. You're going to pause the video and you're going to copy the diagram down, taking up roughly 2/3 of your page. Okay, off you go. Now, through the magic of editing, you have had as long as you've needed on that, whereas I've moved on immediately. You should now have in your notes a date, a title, your key definitions, a diagram of the Earth's structure, and now we need some way of just checking that you understand things. So, new task is going to replace my beautiful face. Match those up. Have you done it yet? Come on board. Shouldn't take too long. If you need more time, you can pause the video. So, what you should have, the thin layer of solid rock, that is the crust, and that is 5 to 70 kilometers thick. The ball of solid iron is the inner core, and that is 1,200 kilometers thick, sorry. The layer of molten or plastic rock is the mantle, that's 2,900 kilometers thick, and the spinning layer of molten iron and nickel, without which no life on Earth would be possible, that is the outer core and is 2,400 kilometers thick. Okay, so that's quite simple, quite easy. As I say, as an introductory lesson, I'd be taking a lot of questions from one person who immediately springs to mind. Comment down below if you know who I'm talking about, year 8. And then I'd finish with something simple, a little bit like this task here. This will zoom out on the exit card, and what I recommend you do, you copy it out, use the box at the top to fill in the blanks, and I will go through the answers in the next video. So that is pretty much what I would be doing in my classroom. There'd be quite a bit more sarcasm, there'd be a bit more back and forth, and the videos that I would be used, I'll put a link to some of the videos, or I'll try cards. There's loads of new things I can explore. I'll put up the videos that I would usually play in lesson. Hopefully this has been useful to you. I'd love for you to share it with friends, colleagues, people who need 10 minutes peace from their children. It's going to be something that I'm going to find a bit more easy to do. So if this is something that you want me to go into a bit more, or if there are particular subjects you want me to do, particular modules you want me to do, plonk it in the comment section down below. And yeah, while you're at it, like and subscribe if you've liked it and haven't subscribed. If you haven't subscribed, why not? If you have subscribed and then unsubscribed, what are we doing? Have I done something to offend you? Anyway, next video should be coming out in a few days, and that will be the next part of the rocks module, and I'll see you then. So until then, my name's Reese, this has been Counting Bubbles, I'll see you soon.